Lesson 2, impulse. It says prove that change in momentum equals mass times velocity change. Well, first of all, Sapicha, you're not on your phone, are you? Calculator, good. We know that I'm in a highlighter. I don't want to be in a highlighter, Mr. Dueck. We know that momentum equals mass times velocity. So it wants us to prove that change in momentum. There is an abbrev in physics and in science for change in. What's the abbreviation or the symbol for change in? Yeah. Triangle. In fact, call it delta. So as a symbol, this is change in. And this is on your formula sheet, but it might be worth memorizing. What's change in anything always? In fact, I think it's the first thing I put on your formula sheet, or one of the first things. Change in anything is always, do you mind, I'm going to abbrev final with an F, minus, and I'm going to abbrev initial with an I. Okay. What does it want us to prove? It wants us to prove that change in momentum is the same as, I'll put a question mark because we're trying to prove that, mass times velocity change. It wants us to prove that this is true. Okay. Maya, what's change in anything? I'm going to try and make the left side turn into the right side. So the first thing I'm going to do is I'm going to go momentum final minus momentum initial, because that's what change in actually means. And then I'll just drop this down, m delta v. And then Lauren, momentum was what times what? Yeah, momentum is what times what? Read the right-hand side, kiddo. Times. So momentum is what times what? And so I'm going to argue momentum final is mass final times, mass times v final, not mass final. Mass doesn't change. Mass times v final minus, and I'm going to argue momentum initial is mass times v initial. And that's going to drop down like a domino. Are they the same thing? Is there an m in everything on the left? There is. I can factor out that m, GCF. I can write this as, and now I'm running out of room, so I'm going to move over here. I can write this as m v final minus v initial, and I'm trying to show that that's the same as that. Okay. Oh, we got a latecomer coming. Pause the video. Person, what's change in anything? So what's final minus initial? So what's final minus initial? No, same thing. Are you telling me that I can write this as m change in v? And that's what I was trying to prove. Okay. One way to write the change in momentum is m times change in velocity. That's very profound. You don't realize it yet, but that's very profound. Here's your new term, impulse. Impulse as is defined as, don't write this down, look up, change in. What's a shorter way to write change in? So if you don't mind, I'm going to do this. Delta and p. What's p an abbrev for? Impulse is change in momentum. Change in momentum is impulse. Impulse is change in momentum. Change in momentum is impulse. They're the same thing. And I'm going to say that a bunch because for some reason I've seen on tests when I ask a kid to find the impulse, I don't know what you mean. It's the change in momentum. What's change in anything? Find the final momentum, find the initial momentum, and subtract them. Okay? In fact, really what the impulse equation is good for, it's a lovely shortcut. So example 1 says, fill in the steps below to find the impulse equation. Take Newton's second law, F equals what? ma, and get the a by itself. We call that Cooper's theorem. A is F over m. Yes? We've done that a bunch. Then take the kinematics equation, Vf equals Vi plus At, and get the a by itself. I can do that. Davin, how would I get the a by itself in Vf equals Vi plus At? Does F over m equal A? Everybody say yes. Does Vf minus Vi over T equal A? Everybody say yes. Well, then they equal each other if they both equal A. In other words, we can now say, hey, F over m is Vf minus Vi over T. Acceleration equals acceleration. I'm probably going to do that soon, yeah. In fact, Davin said, couldn't I write Vf minus Vi as delta V? Yes, and as a matter of fact, what I'm also going to do is get rid of fractions by cross multiplying. Dividing by m on the left is the same as doing what with the m on the right? And dividing by t on the right is the same as doing what with the t on the left? Multiplying, because you guys don't like fractions. This is the impulse equation. It says this: force times time is mass, and then you can either write it as Vf minus Vi. Wait a minute, what's change in anything? What's final minus initial? You know what? You can write it like this, Davin, you're correct. And if we substitute the result from the very beginning, where we also said that m delta V was equal to change in momentum, this is the impulse equation. Change in momentum, also called impulse, can be found in two ways: force times time, or mass times change in velocity. It's kind of a three equations in one. Can you find where that is on your formula sheet? I think it's right next to P equals mv, I think. Is it not? Okay. You don't use all three at once. You use two versions at a time. But impulse is change in momentum. Change in anything is final minus initial. Change in momentum is also, it turns out, force times time. And also, it turns out, it's mass times change in velocity. Which ones do I use? Oh, if they give you or ask for a force and a time, you'll probably use the force and the time version. If they give you or ask for two different velocities, you'll probably use the one with the velocities in it. It's going to be fairly self-explanatory. Don't panic. So what this equation tells us is that a force acting for a time, if you push on something for some amount of time, that's going to make it accelerate, change its velocity. And both of those will cause it, either of those mean you have a change in momentum. It's the same equation we just wrote. I just put stuff in a different order. Now, I have to be honest. This term here, instead of writing it m delta V, usually I'll write it as mv final minus mv initial. Because Jackson, what's change in anything? What minus what? What's change in anything? What minus what? Very top of the lesson, very first thing we wrote. Final minus initial. So m times change in velocity is mv final minus mv initial. I usually go straight to this because it's easier to type on my calculator with no brackets required. Okay? This is sort of a three-in-one equation, three equations in one. You also might notice I'm paying more attention to vector notation than I have been the last couple lessons, especially in forces. We just decided which way was positive, who's winning, who's losing. We did our vector math kind of casually. It's because in momentum questions, because you're often dealing with collisions, after the collision, if they bounce apart, there are changes in direction, and so you'll have to pay meticulous attention, letting one way be positive and one way be negative. Okay? Example 1. A baseball is pitched horizontally due east at 38 meters per second. After it's hit by a bat, it moves horizontally due west at 55 meters per second. Brendan, do you see the word east in this question? Do you see the word west in this question? In other words, are there two different directions in this question? Ding, ding, ding. We're going to have to let one way be positive and one way be. But I'm going to be lazy but organized. What do you want to let be positive, east or west? Pick. I usually would go with east, although you're going to see later on, I'll show you a clever math trick that I usually go with. But when in doubt, sure. So here's what I'm going to do, and this is what I'm going to encourage you to do. Do I want to rewrite everything? No, that's not my style. What did you say is positive? I put a little plus sign in front of the east, and I'll put a positive because that's east. What do I put in front of the word west? And what do I put in front of the 55? Organized, yes. Clear, yes. Lazy, yes. Okay. Brendan, what does A want me to find? So impulse, which is change in momentum, there's two ways to find it. Force times time or mass times change in velocity. Which method do you think I'm going to use here? And this is how you can figure it out. Look at what they gave you. Did they give you forces and times, or did they give you changes in velocities? Lean. I'm going to be using mv final minus mv initial. I'm going to be using m delta v, but I'm going to write it as mv final minus mv initial. And I can figure that out because of the information. If they'd given me a force and a time, I'd use that one. Okay. What's the mass, Brendan? What's v final? Don't say 55. No. Negative 55. And then there's a minus sign, mass 0.144. What's v initial, Brendan? Yeah, yep. What do you get? Now is the time to go to your calculator. You get negative, I'll go negative 13.4. Units. Well, it's mass times velocity. What are the units for mass? You know this. What are the units for velocity? Now, if you left it like that, I'd be okay. But let's write this as a direction. 13.4 kilogram meters per second. East or west? And how do I know? Why must it be west? Because what did Brendan decide negative was going to mean? You decided that. By the way, you could have decided to let west be positive and east be negative. You would have gotten a positive answer, and you would have said positive is west. Now, by the way, usually when we put a direction, what's our abbrev for west? Capital W, but that's also watts and work. So usually when we're writing a direction, we put an at symbol to show that the following letter is a directional component, is telling you the direction that something is going. Or you put it in square brackets. It depends on the notation. I just use the at symbol. Okay. B. Where do you think this impulse came from? Now remember, impulse is also force times time. Don't overcomplicate it. What applied the force to the baseball? Yeah. Okay. If the bat and the ball were in contact 0.8 milliseconds, we'll have to deal with that. What was the average force the bat exerted on the ball? Okay. Ryan, what's C asking me to find? Okay. You could go F equals what? There is enough information here for you to go F equals MA. You can find A by using VF equals VI plus AT. But one of the nice things about the impulse equation is it's a nice shortcut. I'll show you what I mean. Is there a version of impulse that has force and time in it? What? Negative 13.4 equals force times time. I can get the force by itself in one step. In fact, Ryan, how would I get the F by itself? It's going to be negative 13.4 divided by 8 milli is 10 to the what? It's on your green sheet. Negative. Oh, was it 0.8? 0.8 times 10 to negative 3 will work. But yeah, actually 8 times 10 to negative 4 would also be the same thing. Good use of exponents. What do you get? Negative 16,750? If I'd used my, you know what, I probably should have used my answer button, Mr. Dueck. Mr. Dueck, you're sloppy. How did you not use, you had that sitting there. You should have gone divided by, wow, after I've yelled at you all for not using your answer button, I'm embarrassed that I didn't use my answer button. Negative 16,740 if you use your answer button. I'll go to 3 sig figs, negative 16,700 newtons. If they want, did they ask for a direction? I'm not sure whether they want a direction. If you had to give a direction for the force, what direction is the force? If you had to give a direction for the force, is this force towards the east or towards the west? I totally disagree. How do I know it must be towards the west? Negative, right? 16,700 newtons west. Of course it must be west. Think about it. The baseball came screaming in towards the east. East for you folks is to the right. So the baseball came screaming in this way. The force had to bring it to a stop, not just bring it to a stop. It then had to catapult it in the other direction. Yes, you're pushing it to the west, and you're delivering a big change in momentum. Got a reverse for you guys. Sorry, east is to your left, west is to your right. Sorry. So it came screaming in this way. The baseball had to bring it to a stop. People on YouTube are going, I can't see what's going on. Sorry. Come to my class, Nina. And then have it go this way as well. Okay. What's part D asking? Was there a D? Average. By the way, why am I saying average force and average acceleration? Have any of you seen a slow motion, high speed video of a baseball being hit by a baseball bat? Yeah, the ball actually curves around the bat, and it's much more complicated. And so I'm sure the force is not constant during that. And so I'm, as a nerd, hedging my bet and saying, look, I don't think the force is 16,740 newtons the entire time. I suspect we're getting an average. Okay. Oh, sorry, Angus, what did D want me to find? Oh, what did I find in part C? I'm going to go A equals F over M. By the way, you could also go VF minus VI over T, but since I have the force sitting on my calculator, I think I would just go with that. It's going to be negative 16,740 divided by 0.144. Yeah, that's why baseballs take off like a rocket. Negative 116,250. If I wanted to know how many G's that was, how would I convert that to G's? Yeah, yeah. Also, why you wouldn't want to be hit by a baseball bat, delivering a fairly big force. Yeah, and also I've made up some numbers, Davin. I need to actually find a high speed video. I think maybe I'm a little too quick on the time. I think the collision might actually last longer, which would make this number bigger, which would make this number smaller, which would make this number smaller. I'm making up some numbers. I did look up the mass. That's accurate. The 0.144. That's the mass of a baseball in kilograms. Example two. Example two. Hannah, what's 2A asking me to find? Is it asking for a change in momentum? Say no. Is it asking for an impulse? Say no. So don't panic. Momentum is what times what? Yeah, I'm going to keep it simple, stupid. P, not delta P. P is mass times velocity. It's going to be 112 times 3.6. I get 403.2 units. Mass times velocity. Yeah. I think I told you the other day that they're talking about renaming that an Einstein, but it hasn't happened yet. So we still got to write it out longhand. Direction. Well, what direction was the velocity? So what direction is the momentum? Okay. Lauren, what's B asking me to find? Impulse, which is change in momentum. And I noticed they didn't give me a VF. They didn't, well, I mean, they kind of did to a stop. You know what? I'm going to use the most basic definition of impulse, the fact that it's change in momentum. And I'm going to say change in anything, Jackson, is equal to what? This is just going to be the final momentum minus the initial momentum. Now, why am I going with that? Because Hannah, you already found the initial momentum. By the way, if they come to a stop, what's their final momentum exactly as a number? Or 403.2 kilogram meters per second. I guess we're letting south be negative. Well, here's what that's saying. If you're playing football and you want to tackle someone, you have to cancel out their momentum, which is kind of Captain Obvious. Now, there's two ways you can do that. If you're exactly the same mass as the person who's running, you can hit them traveling 3.6 meters per second south and it'll actually exactly cancel out. What if you have less mass and you want to tackle this person? Yeah, you got to run faster. And now you're starting to already see in football why all the different players of different masses play the positions that they play. The smaller mass people, they play further back on defense because they need more time to get up to speed to bring somebody to a stop. The big, huge linemen, two strides and they're got enough momentum that they can bring someone to a stop. They don't need to get to their full speed because their M is bigger, their V can be smaller. For those of you that are football fans, good physics in football. Okay. C. C. Anderson, what's C want me to find? You could go F equals what? You could go F equals MA, but since I just found the impulse, there isn't by chance an impulse equation with an F in it, is there? What? By the way, I think on your formula sheet, did I put a delta in front of the T as well? It's because time is always a change in, but we're lazy. We stop putting the delta. There's two. We do that for two things. Voltage, you'll find, is also always a change in, and we get lazy. We stop putting the delta in front of voltage and in front of time because for me takes this. Get the F by itself. This is actually what Isaac Newton wrote as his Newton's second. I told you Newton's second was F equals ma. He was much more interested in impulse and change in momentum, so he wrote it this way. Okay, it's going to be negative 403.2 divided by 0.8. Oh, do it. Use your answer button. Negative answer button divided by 0.8. I got negative 504. if they wanted a direction and this question wasn't clear. 504 newtons negative is south. Oh yeah, if the person's running north, you have to apply a force southwards to bring them to a stop. That makes sense to me. Do I have any? I forgot to ask. Any football players here, rugby players here, or hockey players here? Okay, those are all situations where you have collisions. Okay. What if the football player brought them to a stop quicker? What if time got smaller? What happens to the impact force? Okay. If you watch football, the really quick collisions where they blow the guy up, oh, that's because the time of impact was so small, you needed a big force to bring him to a stop. The longer ones where they wrap the person up and the person drags them for a couple of steps and then brings them to a stop, those are much gentler tacklers because time was so much larger, the force required to bring them to a stop to cancel out their impulse, not as big. I wrote here, although we solved the previous problem using impulse, we could have solved it using Vf equals Vi plus At and F equals what, Ma. So why am I talking about momentum and impulse? The main reason is it's the best tool we have to analyze collisions. That's next lesson. But there are a few other questions that are most easily answered using impulse. Consider the following example. Example 3. 2 eggs are dropped from the same height h. So both of them, same height. One hits a cement floor and breaks, splut. The second one falls in a pail of water and survives. What's the main reason the second egg survives? Will they be traveling at the same velocity when they get to the bottom of the height? Yes. What? Okay. So we have this. Impulse is force times time. Yes? Which one of these impacts will happen quicker, will last less time? Which one of these will bring the egg to a stop in less time? The floor or the water? The concrete. Well, if that gets really small, what does this have to do so you have the same impulse? If time gets smaller, what happens to the force? Bigger. What about here? Time gets bigger, so force gets smaller. Okay? So let's go like this. Cement, water. On the cement, very tiny time, very big force. On the water, bigger time, smaller force. Does that work okay as an explanation? You'll figure out what we got at? That right there is the physics of all of the recent last 50 years improvements to car crash safety. All we've done is we try and lengthen the time of collisions. Crumple zones, airbags, seatbelts. If we can make time get bigger, then force gets. By the way, what's the final momentum of any car crash ever? What's the final velocity of any car crash ever? So we've got to somehow deal with all of the car's momentum. We have to somehow get it from full momentum to zero. Okay, the bigger we can make time, the smaller we can make the force. And then F equals what? What does damage to us is acceleration. So you're not changing the person's mass, you're changing the acceleration. Mr. Dueck needs to pummel someone, but only for the sake of good physics. Pause the video. Seeing the impulse equation, even though it's not dramatically new, what it does is it gives us a good explanation for most of our car crash safety. In fact, I wrote here, damage from momentum isn't caused by how much momentum is absorbed. It's caused by how fast change in momentum impulse is absorbed. All of you have gone from 100 kilometers per hour to zero. Where? Yeah, and then you get on the off-ramp, slow down a little bit. Then you get onto another road, slow down a little bit more. Then you get into your subdivision, slow down a little bit more. Then you slowly pull into your driveway. Well, you spread that out over so much time, you don't even notice the force. It's there, but it's not like it interrupts your conversation or you have to brace yourself or anything like that. It's spread out over so much time. The force is probably only at most a few hundred newtons, if that. Probably just a few dozen newtons, if that. Okay? So, where has this occurred? Exiting freeway. Here's another way to think about the egg question. Why do they use bales of hay to line some racetracks? What's the advantage in being brought to a stop by a bale of hay instead of a brick wall? Well, if you're brought to a stop, you still have the same impulse, the same mass times big velocity. What's the final velocity of any final momentum of any collision? Zero. So you got to get rid of all of that. You can either have small force big time, or you can have big force small time. Same idea. In many sports that involve striking something, tennis, baseball, soccer, golf, players are told to follow through when they come in contact with the ball. Why might this help the ball leave with a greater velocity? Yeah. So let's suppose I've done weights, I've worked out as much as I can, and I cannot exert a bigger force. What else is in the impulse equation next to the F? If I can increase the time of contact, okay? So as time increases, mass times velocity increases. Does the mass of the ball change when you hit it? So if mass times velocity is getting bigger, which one of those two is the one that's going to get bigger? Yeah. And in fact, any baseball players here? Okay. When you bunt, what do? You actually, or if you play tennis on a drop shot, same thing. You pull back right when you contact. You try and make time so small that it's nearly zero, that almost no force gets transmitted to the ball. And that way, if it's a bunt, ideally it'll drop right down. Or if it's a drop shot in tennis, it'll just barely make it over the net, come right to a stop, and the person has to scramble to try and reach it. Yeah. So, comma, so V increases. Yeah. What has more momentum? A 1,000 kilogram car moving at 100 kilometers per hour, or a 2,000 kilogram truck moving at 50 kilometers per hour? What? I think they're the same. I don't like the units. I would convert the kilometers per hour to meters per second. But even in the units the way they are, if you multiply them together, you'll get the same answer. So I think when you do the conversion, you'll get the same answer. Yeah, they are the same. Does a moving object have momentum? Yes or no? Yes. Okay. Follow-up question, smarty peoples. Does a moving object have impulse? Cody is shaking his head. You know what? A better answer is not necessary, because what? Not necessarily, because what's impulse defined as? A change in momentum. So does a moving object have impulse? Only if V is changing. Sorry, or M is changing. We won't look at a changing mass situation, but a good example of a changing mass situation is when a rocket is burning rocket fuel. Its velocity is constant, but its mass is getting smaller and smaller. We won't look at one like that, though. That really needs calculus, but I should point out, or for that matter, both can be changing. When you jump from your lab table or a playground to the ground, why do you bend your knees when you land? Yeah. Why? What does that do? Oh, what's the final momentum when you hit the ground? Zero. Okay. So yeah. Lean, you awake? And again, watch toddlers when they're 3 or 4 or 5 years old on playgrounds. You can see them figuring out the physics of this. In fact, you might even have seen a little 2-year-old who's just learned how to walk. The first couple of times they jump, they land stiff-legged and with their back kind of bent awkwardly. But then you watch them a couple of months later and they figured it out. Now they're landing and they're bending their knees. you pick up on it because, oh, it hurts otherwise. When you're two, you can get away with it. If as an adult I landed stiff-legged and stiff-spined, I could really injure myself. I'd probably start to break bones. Which of the following situations is more likely to knock out a boxer? Leaning back while taking a punch or leaning in while taking a punch? Why? Ah, time decreases, so force increases. Oh, yeah. Boxers will talk about, yeah, I caught him leaning in, caught her leaning in. All she wrote. So, impulse. Don't overcomplicate it. What's your homework? Every question. You can probably get it all done in class.